Welcome to The Explainer. Today, we're going to peel back the curtain on the technology that powers tools like ChatGPT. We're going to go beyond the hype and really look at the core ideas that make it all work. So let's start with a really interesting puzzle. It gets right to the heart of how an AI thinks, which you'll see is completely different from how we do. Now, this paradox, it's not a bug. It's actually a huge clue to how the whole thing is built. Okay, let's dive in. To really get AI, we first have to wrap our heads around a problem that both our brains and these models have to solve. And that is, how do you find patterns and connections in an instant without searching through every single memory you've ever had? I mean, think about it, right? Your brain just does this effortlessly. You see a face, you hear a song, and boom, instant recognition. But how on earth do you design a machine to do that? Well, the answer, kind of weirdly, comes from the world of physics. The big idea here is what's called an energy landscape. Think of it like a hilly terrain. A physical system, like a protein folding itself up, doesn't try out every possible shape. It just naturally rolls downhill, settling into the deepest valley, its most stable, lowest energy form. It finds the best answer without searching. So what if we could build a digital version of that hilly landscape? That's exactly what we do. For an AI, we can sculpt these valleys to represent things like memories or concepts. So when a new piece of information comes in, the system just rolls downhill into the nearest, most similar valley. It's a form of memory. Okay, so if memories are these valleys, how in the world does an AI actually carve them into the landscape to begin with? Well, this brings us right to the heart of what machine learning really is. The goal of training an AI is actually super simple. It's all about minimizing mistakes. We measure this mistake with a number called loss. The entire game is just to get that loss number as low as you possibly can. The model's parameters are just coordinates on another landscape, and the goal is to find the absolute bottom. So, and this is the key takeaway, learning for an AI is literally just this process of rolling downhill over and over again. An algorithm figures out, okay, which way is down from here? And all the parameters take one tiny step in that direction. You repeat that millions, even billions of times, and that's it. That's learning. And this quote from Bernard Wittero really nails the breakthrough that made all of modern AI possible. A process called backpropagation is just this incredibly efficient way to find that downhill direction for millions or billions of parameters all at once. It's just fantastic. Okay, so we've got the how. They learn by rolling downhill. But now let's talk about the what. What are they actually learning with? And this brings us right back to our original puzzle about that single extra space. See, AIs don't see words or letters the way we do. They see the world broken up into these things called tokens, basically common chunks of text. To an AI, the token for powerful and the token for powerful, with that space in front, can be two totally different things. They get two different ID numbers, and that is why one little space can throw it for a loop. It's pretty straightforward, really. Each unique token in its vocabulary, and we're talking tens of thousands of them, gets its own special ID number. That's the very first step, turning language into math. Then, each of those numbers gets mapped to a vector. Think of it as a set of coordinates, a point in space. But this isn't our normal 3D space. Oh no, this is a space with maybe thousands of dimensions. We call this vector an embedding. It's the model's first guess at what that token means. Now, here's where the magic really starts to happen. As the model is training, as it's rolling down that loss landscape, it starts organizing this giant high-dimensional space. It arranges all the tokens so that moving in certain directions actually starts to mean something. Like this direction might mean plural, another might be gender, or even the relationship between a country and its capital city. And the result is, well, it's just amazing. The model learns these relationships so well that you can literally do math with concepts. The vector that gets you from man to king is almost the exact same mathematically as the one that gets you from woman to queen. It's incredible. So these embeddings are a fantastic starting point, but the meaning of a word isn't fixed, is it? It changes dramatically based on all the other words around it. The model needs a way to handle that. Exactly. Take the word Harry. If the model sees the word wizard nearby, it needs to kind of nudge the meaning of Harry toward the concept of Harry Potter. But if it sees words like queen and Sussex, it needs to shift that same Harry vector over toward Prince Harry. Context is everything. And this is where we get to the absolute engine of modern language AI. It's called the attention mechanism. What it does is it lets every single token in a sentence look at every other token and ask, hey, how important are you to my meaning right now? It's a way for the model to dynamically soak up all the relevant context and create a much, much richer understanding of the text. All right, we've covered the basics, but now we're heading out to the frontier. This is where things start to get really weird and where the old rulebook has basically been thrown right out the window.
You see, for decades, there was this simple rule in machine learning. It was called the U-shaped curve. The idea was that there's a Goldilocks zone for a model size. If you make it too big, it stops learning general patterns and just starts memorizing its training data, noise and all. This is called overfitting, and it was always seen as a bad thing.
So the thinking was, to avoid that, smaller is better, right? This was the undisputed wisdom that guided the entire field for years. Making a model bigger beyond a certain point was just, well, it was considered a mistake. But then, researchers just kept making the models bigger, way, way past that point where they were supposed to fail. And something absolutely shocking happened. After the performance got worse, it suddenly started to get better again, dramatically better. This discovery, called double descent, is a key reason why just scaling up models has led to such incredible breakthroughs. And this brings us to the biggest unknown of all. We have successfully built these incredibly powerful systems, but, as this quote from Chris Olah points out, their inner workings are still largely a complete mystery to us. The concepts represented in those billions of parameters, it's like a kind of digital dark matter. We know it's there, but we can't really see it. So that leaves us with a pretty profound question, doesn't it? If we don't fully understand how these vast digital minds actually work, how can we truly know what they're capable of? That is the fundamental question driving this entire field forward, leaving us to wonder what other surprises these complex systems might hold. That's what we're all waiting to find out.